So, okay, all right. Good afternoon and good morning, everyone joining from other time zones, evening maybe. So welcome to the One World seminar today. We're very happy today to have Professor Yuan here. So he is an assistant professor in the Department of Statistics and Actuarial Science and Department of Mathematics at University of Hong Kong. So before joining Hong Kong he was at UCLA, Department of Computer Science, working with Professor Gu Chen, and he obtained his PhD in the program in applied and computational math at Princeton University, and working with Professor Liu Han and Erwin. So Yuan has done a lot of very interesting work in machine learning theory, in particular learning theory, high-dimensional data analysis, optimization. And today is a very interesting title here, Understanding Deep Learning Through Phenomena Discovery and Explanation. So let's welcome him.
Thank you, Xinhou, for the invitation and the introduction. And hello, everyone. Today, my topic is understanding deep learning through phenomena discovery and explanation. So we know that deep learning has achieved great success in many different applications, right? However, there has been a huge gap between theory and practice, and currently our theoretical understanding of deep learning falls far behind, right? If this image illustrates the current status of deep learning applications, perhaps the current status of deep learning theory can be illustrated in such an image, right? So we can see that there's a huge gap between theory and applications. And everyone working on deep learning theory has been wondering how we can bridge this huge gap between theory and practice. So recently, many researchers have tried to bring up the phenomena discovery and explanation as something that can bridge theory and application. So the idea is that many phenomena we can observe in deep learning can directly help us to develop more efficient deep learning methods in various applications. Well, at the same time, it is an interesting research direction to try to explain this phenomena in theory, right? And trying to explain such phenomena we can observe in deep learning practice can help us to find the better directions in deep learning theory, right? So in today's talk, I will discuss my recent works trying to study phenomena discovery and explanation in deep learning. So I will mainly focus on two of my recent works. The first work is about the phenomena of benign overfitting in convolutional neural networks, and the second work is about the generalization gap between Adam and the stochastic gradient descent. I will also very briefly introduce two additional phenomena I have studied in recent works about the uniform margin phenomena in batch normalization, and then the double descent and multiple descent phenomena in over-parameterized learning. So I will first start with the first part of the talk about benign overfitting in convolutional neural networks. The benign overfitting phenomena refers to the phenomena that when we train an over-parameterized neural network, then in many cases we can actually achieve approximately zero training loss. While at the same time, the test loss can also be small, right? So, so this benign overfitting phenomena has been long understood as some rather surprising phenomena, as it kind of slightly contradicts with our classic understanding in statistics, because overfitting is usually considered as something bad, right? When we overfit, we expect that although the training loss can be easily minimized, the test loss may become worse, right? However, people have observed in deep learning, right? It is kind of okay in many applications to use a heavily overpriced neural network, because somehow benign overfitting can happen, right? So compared with this benign overfitting phenomena, we can similarly define the concept of harmful overfitting, right? And this harmful overfitting phenomena represents the case where the training loss is still approximately zero, while in this case, the test loss is large, right? So in our work, we basically try to provide some understanding or explanation about when and why do benign and harmful overfitting occur. So to answer this question, in the following, I will present our experiment design and the phenomena observation. And then based on the phenomena design, experiment design, the phenomena observation, what kind of intuitive explanation of benign and harmful overfitting we can provide. And then I will also discuss how we can formulate the intuitive explanation into formal theory. So I will first start with the experiment design. So let's consider a very simple experiment, right? Consider a classic example of classifying MNIST data with a convolutional neural network. So here in this image this image gives several examples of the MNIST images. We can see that the MNIST images are handwritten digits, right? And the task for MNIST classification is just to try to classify each handwritten digit to the corresponding class, like 0 to 9, right? So for such a task or learning problem, we can consider using such a CNN model, right? You can see here we have a very detailed CNN model. However, in fact, in our study, I would like to say that this particular neural network architecture is not very essential. Right. What's essential is that we know that training such a CNN model can achieve 100% training accuracy, right? So this basically means that this CNN architecture is complicated enough or overparameterized enough to achieve overfitting, right? And more importantly, we also know that if we train such a CNN model on the classic MNIST data set, actually, we can obtain around 98% test accuracy. So this is clearly a relatively high test accuracy already. And we can conclude that if we really just train this CNN model on the standard MNIST data set, then we will achieve benign overfitting, right? So, so in order to obtain some more understanding about benign overfitting and harmful overfitting, starting from this point, right, we can further consider how we can modify the learning problem, how we can modify the MNIST data set, right, so that the case of benign overfitting can be converted into harmful overfitting, right? Then we can study the conditions for benign and harmful overfitting to occur, right? So that's the idea. So what we consider is that we consider adding noises to the MNIST data, right? So here, these 4 images shows the noisy images with increasing noise level. You can see when the noise level is low, then the digit 2 in this example is still relatively clear to us, right? But when we add a relatively high level of noise, then we can hardly tell that there is a 2 in this image, right? So that's why we believe that perhaps if we add sufficient noise to the MNIST images, then benign overfitting may be converted into harmful overfitting, right? So in our experiments, we basically train the CNN model under different noise levels and using different numbers of training data. And the result can be summarized into such a heat map of test losses, right? So here you can see that in this heat map, this yellow color represents relatively small test losses, and this is clearly corresponding to the case of benign overfitting. On the other hand, the dark blue region of the heat map corresponds to relatively high noise levels. Relatively large test loss values, right? And this clearly corresponds to harmful overfitting, right? So after obtaining this set of results, we basically see that it matches our intuition that when adding sufficient noises to the MNIST data set, benign overfitting can be converted into harmful overfitting, right? And in fact, we can also observe some relation how the test loss is related to the number of training data and the noise level together. So in fact, we also consider another set of experiments. So what we consider is that what if the noises are only added to the boundary regions of the images? So here, these four figures are examples, right? You can see clearly that in this case, the noises are only added to the boundary regions. So the intuition for us to further consider such a set of experiments is that if we compare it with the experiments on the left, right? So we can consider just comparing the high noise level cases. So in this previous set of experiments, we can see that when we add a relatively high noise level of noises, the digit 2 is hardly identifiable to us, right? So this case, it is relatively more difficult for human to do the classification, right? In comparison, in the second set of experiments, even if we have added relatively high level of noises, we can still tell this shape of a digit 2 here, right? So basically, this new set of experiments is relatively easy for human to do, right? However, what we're interested here is that what would be the performance of the CNN model when the noises are only added to the boundary region, right? So a bit surprisingly, we observe that in this case, the heat map of test loss is almost the same as the previous case, right? So here, I need to specify that here to measure the noise level, it is defined as basically the Frobenius norm of the noise matrix added to the image, right? So if we only add the noises to the boundary regions, then essentially to achieve the same noise level, each pixel needs to be added with a slightly larger noise, right? But anyway, if we just define the noise level as the norm of the noise matrix added to the clean image, we can observe that the heat map of test loss in both cases are almost the same, right? So we can conclude that the two tasks have different difficulties for humans, but they present the same level of difficulty for CNNs, right? So after we have such observation, if we look back to the benign harmful overfitting phenomena, we can conclude that the reason for benign overfitting to be turned into harmful overfitting when we add more and more noises, what can be the reason? Can it be that the signals become corrupted or unidentifiable? So based on the two sets of experiments we have done, right, we can conclude that this is not really the reason, right? Because in the second set of experiments, the digits are not corrupted, or at least the major part of each digit is not corrupted by the noises at all, right? But benign overfitting is also turned into harmful overfitting in the almost the exact same way, right? So we can conclude that the true reason for benign overfitting to be converted to harmful overfitting is not that the signals are corrupted, right? So what can be the reason? So our explanation here is that the signals lose a race against the noises. So of course, here I haven't really explained the idea of signals, and I haven't really explained what is the race, right? So in the following, I will elaborate this in detail. So we can treat the clean image as signals, basically, because we know that this clean image, which consists of a handwritten digit like a 2, right? It certainly consists of useful information that are label dependent, right? And we know that it should consist of generalizable information, right? On the other hand, the added noises are label independent and clearly not generalizable, right? So following this intuition, for each training image, right, we can consider to decompose it into a signal part and a noise part, right? So here is an illustration how such a decomposition can be done, right? Should be fairly straightforward. After we consider this, we can do this decomposition for all the 60,000 training data pairs, right? For each training image, we can decompose it into a signal part and a noise part. Then we can imagine So because the CNN is sufficiently overparameterized, right? There actually should exist such a CNN model F1X, such that F1X can map all the signal part of the training data to the correct labels, right? So the existence of such a CNN model is clear because we know that we can consider training the CNN using only the signal part of the image, right? So essentially, you can see that this F1X is essentially trained on the classic MNIST dataset without any modifications, right? And we know this F1X can achieve benign overfitting, and it in fact focuses on signal learning, right? So on the other hand, there also exists another CNN model F2, such that F2 maps each noise part of the training data to the label of the training data, right? So you can imagine the existence of F2 can be demonstrated by training a CNN model using only the noise part of the image together with the label, right? And because the CNN class is sufficiently overparameterized, after training, we can obtain a CNN model satisfying this set of equations essentially, right? So clearly, this F2X trained in such a way will achieve harmful overfitting, right? Because if you look at how it is trained, it has never seen any real handwritten digit at all, right? It has only seen a bunch of meaningless noises together with some labels, right? So there's no way that it can correctly predict the label of some test handwritten digits, right? So that's why F2 should achieve harmful overfitting, and we know that such a CNN model focuses on noise memorization, right? So in summary, F1X learns signals and achieves benign overfitting, while F2X only memorizes noises and achieves harmful overfitting, right? So therefore, whether benign or harmful overfitting occurs depends on how much signals the model learns and how much noises the model memorizes. And importantly, for overparameterized models, right, we know that learning signals or memorizing noises can both eventually achieve overfitting, and as a result, actually the training will stop, right? So what does this mean? So I will elaborate it as follows. So let's suppose that we are at a low noise level, right? So in this case, we can expect that the CNN learns signals faster, right? Imagine the noise is almost zero, right? So the CNN will definitely learn signals faster. And what's the result? The loss will be minimized as soon as sufficient signals are learned, right? Because we know that even if the CNN purely learns signals, it can still achieve overfitting. So the noise will for sure be minimized just based on signals, right? And as a result, the gradients will be near zero before too much noises are memorized, right? So in the low noise level case, even if you continue the training process, like train infinitely many iterations, right? So you won't be able to memorize too much noises because in the late stage of training, the noises, the gradients will be almost zero because you have memorized this, you have learned signals, right? So you won't be able to memorize too much noises, right? So in comparison, in the high noise level case, the CNNs will memorize noises faster, right? And then the loss will be minimized as soon as sufficient noises are memorized. And then the gradients will become near zero before sufficient signals are learned, right? So these two diagrams basically is our explanation of the risk between benign and harmful overfitting, or the risk between signal learning and noise memorization, right? So we can see that benign or harmful overfitting is indeed determined by a risk between signals and noises, right? So this is the explanation we provide for benign and harmful overfitting. And notably, this explanation is based on the unique nature of over-parameterized models, and it is fundamentally different from the classic machine learning theory for small models. Right. So this is the explanation we provide, and in the following, I will then try to formulate the explanation into more formal theories. So in order to establish theories, right? So the first thing we need to do is to do some simplification, right? So we will first consider a simplified model of the image classification task. So essentially, we want to define a joint distribution of the image X and the corresponding label Y, right? So recall that in a CNN model, each CNN filter goes over different spatial locations of the input image, right? So motivated by this, we propose the image classification model as follows. So first of all, we consider binary classification where the label of each image is given as +1 or -1 equally likely, right? And then given this label Y, the corresponding image, we assume that it consists of multiple patches. And the sum of the patches, we assume that they are signal patches given as Y times some fixed vector mu. And the other patches are noise patches generated as Gaussian random noises, right? So we can see clearly that such an image model is trying to mimic the intuitive explanation we provide. So basically, we kind of model the signal patch as something that is related to the label of the data, while the noise patches are something that is irrelevant or independent of the label of the image, right? So this is how we simplify our model. And we consider training a CNN based on n such data pairs x1, y1 to xn, yn. And we also consider a corresponding two-layer CNN model. So basically, we consider a two-layer CNN model with a single convolution layer, basically. And this convolution layer consists of two M filters. And the second layer parameters of the CNN model, we assume that they are just fixed as plus or -1 over M, where M is just related to the number of CNN filters, right? So essentially, there will be M CNN filters whose second layer parameters are 1 over M, and there will be another M filters whose second layer parameters are -1 over M. So, and this is the CNN model we consider. And specifically, in terms of convolution, right, we assume that this CNN model, the convolution filters just go over these different patches of the data we have assumed, right? So each CNN filter will go over the different signal patches and the noise patches contained in each input image, right? So this is the corresponding two-layer CNN model. So, and here we consider the Hilbert-West ReLU activation function, which is the smooth version of ReLU, right? And based on this, under this problem setting, we have the following theorem. So suppose that the dimension is sufficiently large and that we choose a suitable learning rate and suitable weight random initialization scale. So essentially here, we can assume that the learning rate and the weight random initialization scale are both small enough. Then we have the following results. So there exists a function, which is a function of the noise level, such that with high probability, if the sample size is kind of larger than the function of the noise level, then the CNN trained by the gradient descent will achieve approximately 0 training loss and approximately 0 test loss. So on the other hand, if this red condition holds, then the CNN trained by gradient descent achieves approximately 0 training loss and constant order test loss. Right. So we can see that clearly these two parts of the conclusions correspond to benign and harmful overfitting respectively, right? And we can also see that this green condition and the red condition, they are almost complementary to each other, right? So this means that we have established a relatively comprehensive characterization of the benign half overfitting of two-layer CNNs, right? So, so our results basically indicate that the overfitting models may be particularly useful for learning problems with low noise levels, as we can see, right? Because when the noise level is low, then essentially we will only need a relatively small number of training data points to achieve benign overfitting, right? And I will briefly explain how we developed the proof of the theorem. So despite the simplifications we have made, the proof is still quite challenging, I would say. The reasons are that our data model is still quite complicated, I would say, and the CNN model is also relatively complicated, and the training procedure by gradient descent is essentially corresponding to a non-convex optimization problem. And the generalization analysis of such overfitted models are in general pretty challenging, right? So luckily, we have already obtained some very intuitive explanation why this phenomena should happen, right? So following our intuitive explanation, we can find a direction. We can first establish such a proposition, actually. And the proof of the proposition is actually pretty simple. So the proposition states as follows. Let WT be a convolutional filter in the CNN model at iteration T. Then WT has a unique signal noise decomposition given in this equation here. So you can see here, we are decomposing WT during training as a linear combination of its random initialization at iteration 0 and the signal vector mu and the noises in the training images cosine i's. Right. So basically we can show that such a decomposition always exists and is unique, right? So after we have established such a decomposition, we realize that we can utilize this coefficients gamma to represent how much signals the specific convolution filter has learned and how much noises the corresponding convolution filter has memorized, right? Then we can actually further write the gradient descent iterative formula as a discrete dynamical system of the coefficients gammas and rhos, right? And then basically, again, our analysis will then be reduced to the analysis of this discrete dynamical system of these coefficients, and we can basically develop some analysis methods to basically precisely characterize this dynamical system to determine under which conditions gammas will win the race and under which conditions rhos will win the race, right? And that's how we basically prove the theory. Okay, I will then move on to the second part of the talk about the generalization gap between Adam and SGD. So I will first briefly review the Adam and SGD algorithms. So suppose that we are trying to train the neural network with W that minimizes the loss function LW, then the two algorithms are defined as follows. So here is the definition of SGD with momentum. So here we use GT to denote the stochastic gradient of the loss function at iteration T, right? Then basically these two equations defines the SGD with the momentum algorithm, which is rather standard. In comparison, Adam algorithm is defined on the right. So again, GT denotes the stochastic gradient at iteration T. So we can see that compared with SGD, Adam introduces another quantity VT here, right? So this VT here is used in the update of the weights as some sort of modification on the momentum quantity we have calculated, right? And notably, this division operation actually together with the square root operation, all these operations are entry-wise operations, right? So we can see that all the difference between atom and SED is this entry-wise operation utilizing this VT here, right? So, so in conclusion, the major difference between atom and SED is that atom entry-wisely modifies the gradient, or we can say that we can consider this eta and this denominator of square root VT as some sort of entry-wise adaptive learning rate, right? So essentially, we can say that atom utilizes some entry-wise adaptive learning rate compared with SED, where each entry utilizes the same learning rate. So this is the difference between SED and atom. So notably, it has been observed that there can be a generalization gap between atom and the SED, especially in image classification problems. Right. So here, these curves are the results of the test error on CIFAR 10 dataset. So these results are given for ResNet 18 network trained by SED with momentum and atom respectively. And we can see that the final result, STD with momentum achieves approximately 5% test accuracy, while atom achieves approximately 7.5 test error, right? So you can see here is a relatively clear gap considering that these test errors are already quite small. So 7.5 compared with 5 is still quite large, right, in some sense. So what we study in our work here is how can we understand and explain this generalization gap. So I will again present first present our experiment design, the phenomena observation, and then try to provide an intuitive explanation, and then discuss how we formulate everything into formal theory. Right. So our experiment design is as follows. Again, our experiments are actually very simple and very easy to do. So we consider an extremely simple case where we just have one sample from the noisy MNIST data set. Right? So here you can see it's an example, or it's actually the only training data we have used. In this training data point, the image is such a 2 image with noises added to the boundary regions, and the corresponding label is 2, right? So here, basically in this image, the noises are small positive noises, and the noises are only added to the boundary region, right? So we can compare what if we train a simple network using atom and SED when we only have this one training data point, right? So we train a 2-layer fully connected neural network, right? And what we do is that we study what can be learned by a hidden neuron of the 2-layer network. So here we have illustrated in this figure the meaning of one hidden neuron, right? Because each hidden neuron is associated with several weights in the first layer of the 2-layer network. And so we just want to figure out what can such weights learn from this single data point in the data set, right? So note that during training, the weights are iteratively updated, and we should have W1, W2, and in general, WT, a sequence of weights, right? So to study what can the hidden neuron learn, we can investigate the difference between 2 adjacent iterations. For example, we can investigate what is WT plus 1 minus WT, right? And this is essentially illustrating what can be learned during one step of gradient descent or one step of add-on, right? And notably, we realize that the WT plus 1 minus WT has the same shape as the input image, right? So it is convenient for us to just visualize WT plus 1 minus WT as if it is an image, right? So this is what we will do, right? So for SCD with momentum, we basically want to visualize WT plus 1 minus WT as if this difference is an image. And this is actually the visualization result. So we see that here the visualization is essentially just I can say it is exactly the same as the only training image we have, right? So essentially the visualization of WT plus 1 minus WT is just the visualization of the only training image, right? Which is intuitive if you consider the fact that the training objective function is essentially a function of the inner product between W and X, and X is just one fixed image, right? So the gradient of W is parallel to that image. So if you visualize it, visualizing this is kind of visualizing this difference is kind of the same as visualizing the gradient, right? So and the gradient is parallel to the image. So the visualization after standardizing the pixel values, right? Essentially, you are just visualizing the image. So this is what happens for SCD with momentum. So how about Adam? So in fact, for Adam, the visualization result looks like this, right? So you see that here we have a bunch of very white regions. So here, the part I'm highlighting with my this red color, right? This part is not outside of the image, right? It is part of the image or part of the visualization. This part basically corresponds to the boundary region where small noises were added, right? You can see now if we use Adam algorithm, so this is originally small noise entries are amplified, right? So you can see basically this visualization is in some sense binary, right? You can see the pixel values are kind of either 1 or 0, right? So this is basically because of the entry-wise operation we have in Adam. So essentially, this entry-wise division with square root of V is kind of normalizing each entry, the gradients of each entry to the same level, unless the original gradient entry is 0, right? So that's actually the reason why after we visualize the update of Adam, we obtain such kind of a binary image, right? So with this observation and together with our intuition about the signal learning and noise memorization we have discussed in the first part of the talk, right? I suppose the difference between Adam and SCD is rather clear, right? So basically, the entry-wise adaptive learning rate implemented in Adam can potentially amplify weak noises and weaken strong signals, right? And following this explanation, right, we can expect that Adam performs significantly worse than SCD when the data consists of sparse but entry-wisely large signals and dense but entry-wisely small noises. So this is basically the explanation we provide in our work, and now I will discuss how we formulate everything into theory, right? So we actually still implement the same data model we have studied in the first part of the talk, but here we add some additional assumptions, right? We'll assume that the signal patch is sparse, but the non-zero entries are large. In comparison, the noise patch, they are dense but entry-wisely small, right? So this is the image model we consider. And for this model, we have the following theorem result. So under certain conditions, the following result hold with high probability. So Adam will give a CNN model with approximately 0 training error and approximately 0.5 test error. In comparison, gradient descent will give a CNN model with approximately 0 training error and approximately 0 test error. So you can see that in our data model, recall that we are considering binary classification, right? So if the test error is approximately 0.5, then essentially the performance of the trained CNN model is no better than random guess, right? Because if you randomly guess a +1 or -1, the accuracy or error is still 0.5, right? So here, so we can see that in our constructed data model, we have basically constructed an extreme case, right? In this extreme case, Adam will basically almost completely fail, right? No better than random guess. In comparison, gradient descent achieves benign overfitting and basically achieves a small test error, right? So this is our theory. So we can say that this theoretical guarantee perfectly backs up our explanation, and you can imagine what's our proof, right? Although I suppose I don't need to really go over the proof, as the intuition and the phenomena observation is already straightforward enough to expect what kind of proof we implement to get such results, right? So this result actually also partly explains why the generalization gap between Adam and the SED is clearer, mainly in image classification tasks. Because in image classification, perhaps it is more natural to assume that the signals are relatively sparse, and the large part of the image, large proportion of image pixels are perhaps something not directly related to the label of the image, right? So that's why perhaps Adam performs particularly worse than SED in image classification tasks. And I would also like to emphasize that our work here is not trying to claim that Adam is always worse than SED, right? So we basically just try to discover a condition or explanation under what kind of circumstances Adam will perform worse. And we also know that Adam is very popular, right? Together with its modified version, Adam W, right? They are very popular optimization methods for large language models, right? So perhaps for large language models, we do not have such sparse signals and dense noise features. So that's why Adam or Adam W perhaps perform better on those tasks, right? So yeah, that's the second part of the result. And I will then move on to briefly discuss some additional interesting phenomena we have studied. The first phenomena is about uniform margin phenomena in batch normalization. So in this work, we basically considered the classification problem of cat versus dogs in the CIFAR10 dataset, right? So basically, we can convert this task into a binary classification task where the class cat is represented by +1 and the class dog is represented by -1, right? Then we can train a VGG16 network with and without batch normalization with scalar output. So in this VGG16 network, if the function value is larger than or equal to 0, we predict that the label of x is +1 or cat, right? On the other hand, if f(x) is smaller than 0, then we predict that the label of x is -1 or dog, right? So with this notation, we can basically study the so-called uniform margin phenomena. So what we do is that we train this VGG16 network by minimizing the cross-entropy loss over basically 10,000 training data points. And throughout training, we monitor the change of the variance of these quantities, y1 fx1, y2 times fx2, until y 10,000 times fx 10,000, right? So these values are margins achieved by the VGG16 at each data point, right? So, and our observation on the change of the variance of margins throughout training for the VGG16 network with and without batch normalization are illustrated in this image here. So we can see that it is very clear that if we add batch normalization to VGG16, the variance of these margins are significantly smaller compared with the variance of the margins for the VGG16 without batchalization, right? So I think this difference is rather clear based on this figure here. And we basically can conclude that neural networks with spatialization tends to achieve more uniform margins. And adding batchalization can help enforce the network to treat different training data points more equally, right? And in this work below, we provide the rigorous theories about this implicit bias towards uniform margin for batchalization in linear models and two-layer linear convolutional neural networks. So here I won't go over too much details about our proof, but I just want to say that this is a relatively interesting phenomena, I would say, right? So the next phenomena I would like to talk about is the double descent and the multiple descent phenomena. So a double or multiple descent phenomena refers to the phenomena that as the number of parameters in a model increases, the test loss may increase and decrease multiple times. This observation of double and multiple descent phenomena has been proposed by several papers, and specifically a recent work by Song Mei and Andrea Montanari in 2020 studied the double descent phenomena of random feature model. The random feature model is illustrated in this figure here. So essentially, a random feature model can be treated as a single hidden layer neural network. But in this neural network, the first layer parameters are not trained, but they are fixed at their randomly generated values. So the theta part of the parameters are not trainable. And in the random feature model, we only train the second layer parameters A here. So basically, if we consider training this model on some certain type of synthetic data, we can obtain such a curve illustrating the relation between the test loss and the number of parameters n. So you can see clearly this curve of test loss first decreases and then increase and then decreases again, right? So this is double descent, right? So what we study in one of our recent works is that we consider a very simple modification. What if half of the activation functions are changed from ReLU to sigmoid, right? So originally in the experiments in the figure in the previous slide, right? That result are corresponding to a random feature model with ReLU activation function. But here, what if we consider such a random feature model where half of the activation functions are still ReLU, but the other half of activation functions are sigmoid instead? So in fact, if we consider training such a random feature model on the same synthetic data as the previous experiments, we realize that now we can observe triple descent. As you can see, this is the curve of the test loss. It decreases and then increase and decrease again, and then increase again, and then decrease another time. So this is triple descent, right? So we provide an intuitive explanation for this triple descent phenomena in the work here published on JMLR recently. And actually guided by our theory, we are also able to discover quadruple descent and quantable descent, right? So in general, we can conclude that there exists a random feature model with k types of activation functions that exhibits k+1 fold descent. Right, so this is another interesting phenomena I would like to briefly mention. All right, and that's all for my talk. Thank you very much.
All right.